Hello everyone, welcome to HC Tutorials, and today we are continuing with free body diagrams. This is part 2. So let's say we are asked to draw a free body diagram of a box being pulled at an angle on a horizontal rough surface. Okay, so to answer this question, we already know that there is a force that is acting downward. We call it the force of gravity that is acting downward. And we also know that there is a force that the surface exerts on the box, which is the normal force. This is the force of gravity. Okay, and then we also have this force here. Okay, and we also have another force because this is a rough surface. We know that we have another force, which is the force of friction. Okay, so let's draw our free body diagram. When we draw our free body diagrams, we're going to represent our box with a dot as usual. Okay, and then we put our force of gravity, which is acting downward. Okay, and then we put a force that is equal to that force, which is the normal force, Fn. Okay, we also see that we have the frictional force. We put in this direction, we put our frictional force. Okay, and then we have the force applied, but it's applied at an angle. So we draw it into that direction at that angle. Okay, and level it. This is the force applied. And I always tell my student to keep it simple as possible. So if your teacher taught you how to componentize and do that, it's okay, but I would advise you to go down this way. Okay, so now what is the net force? Okay, let's look at our horizontal plane. Okay, horizontal plane. Okay, when we look at our net force, looking at our horizontal plane, we know that we'll be looking at forces that are acting on this plane. Okay, our horizontal forces are what? Acting on this plane. Okay, so but as you can see that this applied force is applied, it's not there by the horizontal plane, but it's applied at what? At an angle. It's going up. Okay, and it's also not there by our vertical plane. Instead, it's at an angle, which is the angle is theta. Okay, so now when we look for our net force, which is the net force equal to, we are not going to use this force as it is because it is not on our horizontal plane. It is not here. Okay, so we need to break down this force into two components. Okay, let's say this is our force. This is our force, Fa. Okay, this force is divided into two components, which are the horizontal component. Okay, we call it the Fx, and also the vertical component. Okay, which is Fy. Okay, so these two forces, if I have to represent them here, let me just erase this so that you can see clearly. Let me just erase some part. Okay, I want to represent these forces here. These forces are here. This is our horizontal component, which is the Fx, and then our vertical component will be going up like this. Okay, it means now when we look at our net force along the horizontal plane, instead of using our force applied, we're going to use our what? Our Fx, which is the horizontal force. And this horizontal force, the horizontal force in this case equals to our Fa, which is this one, the force applied, cos of theta. Okay, So when we calculate our net force, we're going to say our force applied, the net force equals to our force applied minus the frictional force, because these are the forces that are on what? Our horizontal plane. Okay, but because our force applied, the force applied is applied at an angle, we will substitute our what? Our horizontal force, which is what? Our Fx. So we're going to say our net force equals to, what is our horizontal force? Fa cos of theta minus the frictional force. And that's how you're going to get your what? Your force net, or your net force on your horizontal plane. Okay.